Hello everyone, welcome back to Z Physics. Today we are going to be doing a revision lesson on materials. So let's get started. The first thing that we need to revise is actually the definition of tensile and compressive forces. So remember, tensile forces actually produce extension. So that means that we're essentially trying to stretch an object. For instance, if I was to apply a tensile force onto this material over here, this would stretch under the tensile force. A compressive force would tend to reduce the length of the material. It would, in other words, shorten it or compress it, like so. So this over here would be an example of a compressive force. And this leads us up to Hooke's law, which is the next point in the A Level Physics specification. So Hooke's law says that the applied force is directly proportional to the extension. In this case, F stands for the applied force. So we can just write this down. This over here is the applied force, which is measured in newtons. X is our extension, like so. Remember, extension would be found by subtracting the final length from the initial length. I can just write this down, maybe here, length final minus length initial, and K is the spring constant, which is also often called the force constant. So let me just write this down like so. So this over here will be the force constant. Now, what are the units of the force constant? K will be F divided by X. So F is measured in newtons and X is measured in meters. Therefore, K will have units of newtons per meter. Now let's have a look at an experiment in order to demonstrate Hooke's law and hopefully find the spring constant, or the force constant of a spring. So we have the following setup. Over here we have a stand which is connected to a spring with some masses attached to it that we are going to vary. We're also going to attach just behind the actual stand, probably with a boss and a clamp, ruler just next to the spring. Because we're going to have some masses attached to the stand, it's also much safer to use a G-clamp to attach the stand to our desks. Now the first thing that we need to do is, as we said, suspend some masses from the actual spring. In the following experiment, we are going to be varying the mass and we're going to be recording the extension. Remember, in order to find the extension, all we need to do is to subtract the original length of the spring from the extended length. We're going to find the force for each of those masses using F is equal to mg, and then we're going to plot a graph of the force against extension. In order to make our readings as accurate as possible, we need to make sure that we take all readings at eye level in order to reduce the parallax error in this experiment. If Hooke's law is indeed correct, we expect our results to produce a straight line through the origin. We can actually compare this with the equation of a straight line. We can just do this over here. So F is equal to Kx, this is Hooke's law, Y is equal to mx plus c. We can see that our intercept is 0. X is on, surprise, surprise, the x-axis, F is on the y-axis, and this means that our gradient is equal to the spring constant. So in a force against extension graph, the gradient is equal to the force constant K. Now, what about the area underneath the curve? In order to find the area, we need to find the area of this triangle. In order to do so, we're going to be multiplying force by extension. So that means that we're going to have force times distance, which so once again, the area will be equal to half Fx. Now this will have units of Newton meters. So that means that our area will actually be the work done. Intuitively, this also makes sense because in order to find the work done, we need to multiply the force by the displacement that's been traveled in the direction of the force. So we can say that the area underneath the curve is equal to the work done, like so, which is also equal to the amount of energy, like so. This energy in particular is known as elastic potential energy, and it has the following two formulas. So let's just write this down. So elastic potential energy is the area underneath the curve, which is a half, what's happening here? Let's fix that, a half Fx. But because of Hooke's law, we know that F is equal to Kx, like so. So what I'm going to do is I'm just going to sub that back into the original equation, and what I'm going to get is that elastic potential energy is going to be equal to a half Kx times x, which is equal to a half Kx squared. And those are the two formulas that we know for elastic potential energy. Remember, in an F against x graph, the gradient is equal to a spring constant and the area underneath the curve is equal to the work done, or the elastic potential energy. Let's have a look at stress and strain. First of all, the stress, which is given this symbol sigma over here, is defined as the amount of force that has been applied divided by the cross-sectional area. That means that the stress, which is very similar to pressure, will have units of newtons per meter squared, or you could also measure it in pascals as well for the units. Strain, on the other hand, which is known as in particular the tensile strain, which is applied to stretch really an object, is defined as extension divided by the original length. So let me just write this down. So strain, which is given the symbol epsilon, like so, is our extension x divided by the original length. Just to avoid any confusion, I'm going to just label those. So x in this case is the extension and L is our original length, like so. Because it's going to have units of meter over meter, strain is actually unitless. It is often given as a percentage, by the way. For instance, if our original length was let's say 1 meter, and then it's stretched, let's say 0.1, our strain will actually be 10%. So we can convert that to a percentage, which is approximately equal to 10%. So don't get confused if you come across in a question the strain being given as a percentage. We should be fairly confident just converting those numbers from percentage to a fraction and vice versa. And there's one more quantity that we definitely need to know for our exams, and this is the ultimate tensile strength. Now, this is the greatest amount of stress. I'm just going to underline this because that's really important, that a material can withstand before reaching its breaking point. Quite a common misconception is to just write down a thing that is the greatest amount of force, but remember, if that force is spread over a large surface area, it doesn't really matter. It's the stress which really affects the material. So once again, the ultimate tensile strength is the greatest amount of stress that a material can withstand before reaching breaking point. We can combine those two quantities, stress and strain, into a quantity which is known as Young's modulus, which is given the symbol E in your formula booklet if you're doing OCR physics. And this quantity, Young's modulus, is stress, or in particular tensile stress. This could be important, so let's just write this down. So this will be equal to tensile stress, like so, divided by tensile strain. So tensile strain. Mathematically, this would be just equal to essentially stress, like so, divided by strain. Now remember, our stress is force over area. Then we're going to be dividing that by the strain, which is extension over original length. If I am dividing by a fraction, this is the same as multiplying by the inverse. So this means that Young's modulus will be equal to F divided by A times the original length divided by the extension. Okay guys, now let's have a look at an experiment that we can do in order to determine Young's modulus of a metal wire. The first thing that we need is a table or a desk of some sort, and we're going to clamp a wire, which is given in this blue color, which is running along the desk with a pulley on the end. The reason why we use a pulley, because this way we can keep this part of the wire purely horizontal. Then we can attach a mass at the end of the wire. We are going to be varying this mass M like so. We're going to put a marker on the actual wire with a ruler underneath it. By seeing how much the marker moves, we'll be able to determine the amount of extension in the wire. Remember, F is equal to mg, which is our force, so we'll be able to determine our Young's modulus, which is stress over strain. Remember the force, this will just be equal to mg. For the area of a wire, we can use a micrometer screw gauge to determine the diameter, and then just use pi d over 2 squared. Our extension we'll be able to determine with this setup, with the marker and the ruler underneath it, and our original length of the piece of wire we can just determine with a ruler. Note that often the extension of a metal wire can be very tiny, so we may have to use a traveling microscope if the extension is quite small. So maybe in brackets over here, I'm just going to add this, that we may have to use a traveling microscope like so. In this experiment, we are going to be varying the force F by essentially adding progressively more mass onto the end of the wire. We're going to be measuring the extension X. In terms of measurements, we're going to be, first of all, we'll need to measure the diameter D of the wire with a micrometer. We'll take several readings along the length of the wire in order to ensure that the wire has a consistent diameter all the way along its length, and then we're going to average. We're going to use this to calculate the cross-sectional area A, and for that we're just going to use the cross-sectional area formula, which is just pi r squared, which means that this is equal to pi d over 2 squared, which is equal to pi d squared divided by 4. We're also going to be measuring the original length with a ruler. We are also going to be measuring the extension X with this marker over here and a ruler, or if the extension is smaller than a couple of millimeters, we're going to be using a traveling microscope in order to be really accurate and reduce the percentage uncertainty in our measurements. So just to summarize, we have the force F over here that we're going to measure just using mg. L over here will be our original length that we're going to measure with a ruler. A is our cross-sectional area. We're going to measure the diameter with a micrometer, and X over here is our extension that we're going to be measuring with this setup over here. After we have taken all of these measurements, what we need to do is to plot a graph of the force that's been applied against the extension X. If we remember what we did with the formulae for Young's modulus, which is equal to stress over strain, which is equal to force divided by cross-sectional area, divided by extension, which is then divided by the original length, this will be equal to F over A multiplied by L over X, because dividing by a fraction is the same as multiplying by the inverse. And what we can do is then compare this equation with the equation of a straight line. Remember, if f is on the y-axis, what we need to do is rearrange for this. So what I'm going to say is that f will be equal to Young's modulus E times the cross-sectional area A times the extension X, and we'll also need to divide by the length, like so. So let's just divide by the length, and we can compare this with the equation of a straight line. Remember, y is equal to mx plus c. I'm just going to add a plus 0 because I can, and we can see that the graph should be a straight line through the origin. Additionally, we can see that f is on the y-axis and x is on, surprise, surprise, the x-axis. So our gradient, we can use a different color for this, will actually be equal to this expression. So let's write this over here on the side, that our gradient m will be equal to Young's modulus times the cross-sectional area divided by the original length, which means that our Young's modulus, which is what we're looking for in this case, will be equal to the value of our gradient multiplied by the original length of the wire divided by the cross-sectional area. Okay, folks, so hopefully this experiment makes sense now. Okay guys, now before we have a look at stress and strain graphs, let's define a couple of very important definitions. First of all, what is a ductile material? So this is a material which can easily be drawn into wires. Additionally, we need to define elastic deformation, and for instance, if we apply a tensile stress onto this material over here, if the material returns to its original shape after the force is removed, then this material is elastic. So we can just make sure to underline this because this is really important. On the other hand, in plastic deformation, the material does not return to its original shape or original length after the force is removed. Okay, now let's have a look at some stress and strain graphs. Okay guys, now let's have a look at the stress against strain graph for a ductile material. First of all, up to point P in this first region over here, we can see the stress is proportional to strain. Most of the time the material would actually obey Hooke's law up to point P, which is known as the limit of proportionality. At point E, permanent deformation occurs. So that means that up to point E, which is known as the elastic limit, the material will exhibit or will experience elastic deformation. If you go beyond point E, plastic deformation occurs. So that means the material is permanently deformed when the force is removed. The highest amount of stress that a material can withstand is known as the ultimate tensile strength, and this is this point over here. This over here is our ultimate tensile strength, and eventually if we keep going, we're going to reach the breaking point of the material. So this over here is the stress against strain graph for a ductile material. Let's have a look at the behavior of a brittle material as an example of brittle material. For instance, it could be something like glass, for instance. Okay, anyway, so if we pull out a graph of stress against strain for a brittle material, we're going to see that the graph will be a straight line through the origin all the way up to the breaking point. Now in practice this means that stress is proportional to strain and that Hooke's law is obeyed. Now notice that elastic deformation occurs all the way up to the breaking point. And remember, elastic deformation means the material will return to its original length after the force is removed. Finally, we are going to have a look at polymeric materials, which are made from these long chains of molecules. An example, for instance, is rubber. Now notice that this has a very distinctive shape. For instance, if we are trying to stretch the object from applying a tensile strength, the curve will be like so. However, if we're applying a compressive stress, the curve will be like so. Now notice that this will have elastic behavior. This means that the material will return to its original shape after the force that's been applied has now been removed. In general as well, Hooke's law is not obeyed. We can see that this graph is not a straight line through the origin. Notice that some energy will be lost as well in the process, normally as heat. In terms of polyethene, which is an example of a polymeric material which exhibits plastic behavior. The stress and strain graph initially starts being proportional, and some of them may initially obey Hooke's law. However, quickly you reach a point at which plastic behavior occurs and the material no longer will return to its original shape after the applied force has been removed. Okay folks, so this was the whole of materials. Any questions, please drop a comment down below. Thank you very much for watching, and if you found this video useful, please give it a like and a subscribe. Thanks again, see you soon for the next video.